Hi everybody! So in today's video, we're going to be starting Unit 6, which is going to be all about what's called integration. We have one learning target for today, which is I can evaluate an integral using geometry. So today we're going to be learning about a new calculus idea called evaluating integrals. And today specifically, we're going to learn how to do that evaluation using geometric formulas that we've learned in the past. So let's start by reviewing what we already learned this year. In the first part of calculus, we spent most of our time learning how to find the rate of change of a function. Now, we also learned that there are two different types of rates of change. There's what's called the average rate of change, which we can find by using the formula f of b minus f of a all over b minus a. And as a reminder, this is just like our regular old slope formula that we used to do when we were younger, where we would do y2 minus y1 and x2 minus x1. We also learned about something called the instantaneous rate of change. Now, the instantaneous rate of change is the derivative. So we can find the instantaneous rate of change by finding the derivative of our function using all of our derivative rules that we've learned before. Now, there are a couple important things that we need to know about these two types of rates of change. The average rate of change is going to be the slope of the secant line. So if you draw the line that goes through those 2 points, it's going to be the slope of a secant line that cuts across a graph and touches it in 2 spots, whereas the derivative is going to be the slope of the tangent line, which means that it is the slope at a single spot where it brushes the graph. The other difference between these types of rate of change is that an average rate of change is going to be over an interval, which means we're looking over a span of 2 points of a graph, so we would say that it's from A to B, whereas the derivative is at a single x value. For example, you would use like a specific number, x equals a. So there are a couple big differences between these types of rates of change, and the reason that calculus is kind of helpful is that it's the first time where we're able to calculate the instantaneous rate of change versus what we did before, which was always the average rate of change. Now, in this second part of kind of the format of calculus, the second big topic is going to be about integrals. And an integral is defined as the area between the graph of a rate of change function and the x-axis. It has a special meaning. So it's an area, this is important, it's an area between the graph of a rate of change function and the x-axis. So it's between the x-axis and the function, and it tells us what's called the accumulated change of the function over a given interval. We represent this area using what's called an integral. So what we're going to do right now is go over the new notation. We're going to understand all of the parts of the notation, and then we're going to look at a visual representation of what we're actually finding. So the symbol for integral looks like this elongated S, and the reason it looks like that elongated S is because it comes from the word sum, where you're adding up the areas between a function and the x-axis. The lower number here is what's called the lower bound, and that number tells us the starting x value. So where do you start on the graph when you want to find your area? It should always be the lower number. when your integral is written properly. So the lower bound should always be the lower number. And the upper bound, which is right up here, tells us the ending x value. So integrate means find the area starting from where x is equal to that lower number and ending at where x is equal to the higher number. It should always be the higher number. If your integral is written using the proper notation. Now, the beginning of the notation is this integral. And the end of the notation is this dx. That tells us the variable of integration. So it tells us that our function is defined in terms of x, and we're integrating with respect to x. And by putting that at the end, it tells us that the function that we're looking at is everything in between the beginning of that notation and the end. It kind of tells us like the function you're looking at is in between these two things. I sometimes think about this as like a parentheses. You need a beginning and an end of your parentheses. It's kind of the same thing. Your integral is not complete until you have that dx at the end. The last piece of this notation is f of x. This is going to be the function whose graph you're looking at. So in other words, it's telling you, hey, graph this guy and find the area between that guy and the x-axis, starting from your lower bound and ending at your upper bound. Now, here's what that looks like. If we were looking at the areas here, and I said I want to integrate from negative 2 pi, meaning that's the lower bound, to positive 2 pi, meaning that that's the upper bound, then the areas that we're looking at would be this area, because those are areas between the x-axis and the function, as well as this area down here and this area down here, because those are areas that are between the x-axis and the function. Now, the key here, one of the key things about integrals is that when areas are above the x-axis, they are considered positive. So this area right here would be a positive area, and this area right here would be a positive area. And when areas are below the x-axis, they are considered negative. So this area right here would be negative, and this area right here would be negative. Now, when we go and we actually do some problems on the next page and we look at these areas and we're finding them, that's going to affect the way we find our answers because we're going to need positives and negatives to indicate whether those areas count as above or below. All right, so let's take a look at some example problems. Problem number 1 here says find the integral from negative 3 to positive 2 of f of x dx. So what this means is that my lower bound is negative 3. That means on this graph, I'm going to start where x is negative 3, so right here, and integrate until x is negative 2. So that means I'm going to integrate or find the area until x gets to right here at negative 2. The area between the function and the x-axis, starting from negative 3 and ending at negative 2, would be the area of this little triangle, which is above the x-axis. So right away, I know that that should be a positive area. Now, in order to find that, I'm going to find the area using the formula for a triangle, which is 1/2 times the size of the base. This triangle is 1 unit wide, the base is 1, times the height. This triangle is 1 unit tall, which means my total area would just be 1/2. For problem number 2 here, we're going to find the integral from negative 3 to 0. So negative 3 to 0 means start from negative 3, which is right here, and end at 0, which is right here. So that would be right here on the graph. Now, if we look at this kind of portion of the graph, it's actually kind of divided up into two parts. There's the triangle up here that's above, and there's a triangle that's below. That means that in order to find the value of this integral, I'm going to need to find the area of both of those parts and combine it, the total area. So the first thing I'm going to do is find the area of this little triangle that's above, and that's going to be a positive area. So I'm going to just do 1/2 times 1 times 1, just like I did in problem number 1. Now, to get the area of this orange portion that I shaded, that's going to be a negative area. So I'm going to put a minus here because that's negative and it's below the x-axis. The size of that would be 1/2 times the size of the base, which is 2, times the size of the height, which is also 2. Now, when I find my answer here, I'm going to get 1/2 minus, now 2 times 2 is 4 and half of that is 2. So 1/2 minus 2, which means my final answer will just be whatever I get when I do 1/2 minus 2, which in this case is going to be negative 3/2, which is negative 1/2. You can think about this 2 as being 4/2 in order to think about this with common denominators. So 1 minus 4 would be negative 3/2. Now that makes sense that my final answer is negative because the size of the area that's below here is bigger than the size of the area that's above. So that means that when I find the total area, the final answer is going to be negative because more of that area was below. For problem number 3, we're finding the integral from 0 to 4. So 0 is my lower bound, which means I'm starting my integral from here. And 4 is my upper bound, which means I'm ending my integral right here. That means that I want to find the size of this area. Remember, we're always finding the area between the x-axis, which is right here, and the graph. So even though it kind of looks like this would be a semicircle, that's actually not the area we're looking for. We're looking for the area outside of the semicircle. Now, there is no area formula for like this shape. But one of the ways we can kind of creatively find that area is to think about this as being a rectangle that we removed a semicircle from. So to do this, what we're going to do is the following. First of all, I know that this area should be negative because it's below the x-axis. So I'm going to do negative, and then I'm going to find the area. To find that area, I'm going to start with the area of the rectangle. So I'm going to do the area of the rectangle, which is this whole thing. And the area of that rectangle would be just base times height. So the base would be 4 and the height would be 2. Minus, and in order to find kind of that other portion of the area, I'm going to subtract the semicircle. And that's going to give me the region that's on the outside. So I'm going to do minus the semicircle. Now, the area of a circle is pi r squared. So a semicircle would just be 1/2, half of pi, and then r squared. And in this case, r is the radius would be 2. So in order to get that area that's outside of the semicircle, I'm going to do the rectangle minus the semicircle. All right, so now I'm going to have negative, and then 4 times 2 is 8, minus 4, 2 squared is 4, divided by 2 is 2, so 8 minus 2 pi. And then because those are not, things that I can calculate without a calculator, I'm not going to do 2 pi without one. I'm going to leave it and have a pi in the answer. I'm just going to go ahead and distribute that negative, so I get negative 8 plus 2 pi as my final answer. Now, if you think that pi is approximately 3, 2 pi would be about 6. Negative 8 plus 6 is still going to be a negative number, which makes sense because the size of that area is all below the x-axis, so my final answer should be negative. All right, last but not least, let's say that I want to find the integral from negative 3 being the beginning, my lower bound, to positive 4 being my upper bound. That means that I want this area and then I want to do minus this area, and then I want to do more minusing for this area. Well, the good news is that we can actually use some of the answers that we already found to help us with this. What you should notice is that this picture is just the combination of the picture we drew here and the picture we drew here. So we can use that to help us. To get this total area, we can take the answer from number 2, which will give us this portion of the area. So that's going to be negative 3 over 2. That's from problem number 2. Plus, then we can also take and add in the area that we found in number 3. So this is the area that we found in number 3, which is negative 8 plus 2 pi. And so we're going to be able to find this answer without doing a whole lot of extra work because we already have those numbers to work with. So my answer then is going to be negative 3 over 2 minus 8 plus 2 pi. I can combine these numbers. So 8 is really 16 over 2, which means I get negative 19 over 2 plus 2 pi. The reason I'm not combining that with the 2 pi is that the 2 pi obviously has a pi in it. So it's kind of like not like terms. It doesn't combine with the terms that don't have pi's. All right, last but not least, I picked up too many pages. What do we do if we don't have a graph? So one of the strategies that we can use to find an integral when we don't already have a graph is that we can sketch a graph. So what we're going to go through right now are a couple different examples where we're going to sketch a graph and then find an area. And part of what I'm going to do here is remind you what some of these graphs should look like. So for problem number 5, we want to find the integral from negative 2 to 2 of the square root of 4 minus x squared. Now, anytime you see a square root and then a number minus x squared, that's going to be a semicircle. And the reason that that's going to be a semicircle is that the formula for the circle is x squared plus y squared equals r squared, which means if you solve for y, you get plus or minus the square root of r squared minus x squared. And in this case, since it's only the plus, it's only half of the full circle, it's only the top half. So to sketch this, I'm going to draw a semicircle whose radius is 2 because this is the radius squared. So then the radius would be 2. So 1, 2, 1, 2, 1, 2. I'm going to draw my semicircle. Now I want to find the area between negative 2, which is right here, and positive 2, which is right here. So to get that area, I'm just going to do the area of this half of a circle. So the area is going to be half of pi times r, which is 2 squared, which would just be 2 pi. For problem number 6, if we sketch the picture of the function that is just 3, that's going to be a constant function. It's going to be like a horizontal line. So we're going to go from negative 4 to negative 1, and we're going to sketch a graph of a function at positive 3. Now, in order to find the area between negative 4 and negative 1, which are my lower and my upper bounds, I'm just going to be finding the area of that rectangle. So that rectangle is going to be base times height. The base is 3 units wide and the height is 3 units tall, so the area is 9. For problem number 7, we're looking at a piecewise function, and this piecewise function is equal to x whenever x is less than or equal to 2, and then 3 whenever x is bigger than 2, and we want to integrate from negative 1 to 4. So I'm going to go ahead and sketch a little graph here. So we want to integrate from negative 1, which would be right here, to 4, which would be right here. Now when this function is broken at 2, so I'm going to go ahead and know that there's a different picture on the left side of that number and there's a different picture on the right side of that number. On the left side of that number, my function is just x. So when x is negative 1, y is negative 1, 0, positive 1 is positive 1, positive 2 is positive 2. So this is the graph of my function on the left side. On the right side, the graph is just 3. So if 3 is right here on the right side, it would be 3 going this way. Okay, so we've got our piecewise graph. To find this area, we're going to have to break this up into several different parts. So the first part of the area that I'm going to work with is going to be this little triangle right here, which is below the x-axis. The next part of the area that I'm going to work with is going to be this bigger triangle right here, which is above the x-axis. And the last part of the area that I'm going to work with is going to be this rectangle right here, which stops at my upper bound of 4. So I'm going to go ahead and do this in 3 parts. The first part is going to be a negative area because it's below, and I'm going to do 1/2 times the base is 1 times the height is 1. The next part of my area is going to be a positive area because it's above, and the triangle is going to be 1/2 times the base is 2 times the height is 2. And the last part of my area is going to also be positive because it's above, but it's going to be a rectangle. So it's going to be a base of 2 times a height of 3. So now I'm going to go ahead and just compute the final answer. So I get negative 1/2 plus 2 plus 6. Now, when I combine those, negative 1/2 plus 2 plus 6 would be 8 minus 1/2, so 7.5, which in other words is going to be 15/2. You could also think about this as being 4/2 and 12/2. So negative 1 plus 4 plus 12 would be 15/2. Last but not least, we're going to talk about this function, the absolute value of x over x. Now that is a special function that you need to kind of just know what it looks like. The absolute value of x over x, or if it could be reversed, you could do absolute value of x over x, or you could do x over absolute value of x. It doesn't really matter. You're going to get the same graph either way. Is going to be a function that looks like this. For all positive x values, this function is going to be positive 1. And for all negative x values, this function is going to be negative 1. And you can make one of those close. It doesn't really matter which one. You just need to know that it looks like that. And the reason is because when your x's are positive, the absolute value of x and x are the same number. So you're always going to get 1 when you divide. When your x's are negative, the absolute value and x are opposite numbers. So you're always going to get negative 1 when you divide. In this problem, we're going to be going from negative 1, which is right here, to positive 2, which is right over here. So in order to find this, again, I'm going to break this up into 2 areas, this area that's below, and then this area that's above. Which means I'm going to do, for the area that's below, negative, and then base times height, so 1 times 1. And then for the area that's above, I'm going to do plus base times height, so 2 times 1. Which means I end up getting negative 1 plus 2, which means when I combine those, I just get positive 1. All right, that is your brief introduction to integrals, the idea of finding areas, and I will see you soon for some practice.